Hello and welcome to another tutorial. In this tutorial I'm going to discuss sequences and series. These are important concepts in math and analysis, and I'll discuss how to implement them in Java. Now, a brief introduction to sequences. A sequence is basically a function of integer numbers. So if we have a continuous function f of x, so it's called a continuous function because x is a continuous variable that can span all the way across the real numbers. And then f has a dense relation. The plot of f is basically dense, so it's a dense plot. But then when you look at the discretization of this function over only the integer numbers, you see only dots. So this plot is not a dense. It's not dense. It's a discrete points along the integer numbers. Okay, so this is called a sequence of integer numbers, and it could very well span from negative numbers to positive numbers. And we typically don't use the sequences with f of n. We typically show them as f sub n or a sub n. So we use a subscription we use a subscript index for the sequence instead of writing them as f of the x or f of the n. So an is value of an can be real or complex. So the sequence could be a sequence of integer numbers, which are always real, but then it can map them to real or complex numbers. Okay, so the output of the sequence can be real or complex. Here we just consider real numbers, so the output of the sequence is also a real number. And it can be defined over positive or negative numbers, from negative infinity to positive infinity. But the typical case is that we typically start from 0 index, because if you have negative, you can just shift the index, right? The convention is to use from 0, then go to positive numbers. Sometimes we just start from 1 and go to positive numbers. I guess it's really a matter of choice. And then one example is 1 over n squared, and n starts from 1, 2, 3 to infinity. And then there are two important types of functions. So if you look at this sequence or the representative function, you see that as you increase n, the function increases monotonically. So this is called a monotonically increasing function. So for all n, at each given n, if the next term of the sequence is larger than the current term, it's a monotonically increasing. If the next term could be greater than or equal to the current term, then it's just called an increasing function. It's not monotonic. So monotonic here is a keyword. Similarly, for the decreasing functions or decreasing sequences, if for all n, at each given n, the next term is less than the current term, then it's a monotonically decreasing function or sequence, and the next term could be less than or equal, then it's just a decreasing function. Okay, now one important concept for sequences is the limit, or what happens when the n goes very large, n goes to infinity. Okay, and it's called the limit of the sequence, which is the value of the sequence or the proximity of the sequence to a given number when n is very large. And as n gets larger and larger, the terms of the sequence get closer and closer to that number, which is called the limit of an, limit of the sequence. And here are some examples. 1 over n squared, when n goes to infinity or n gets very large, so the denominator gets very large. So 1 over a very large number is approaching 0. That's why we say that the limit of 1 over n squared is basically the limit of n squared is basically 0. Now the other case is the natural number, or the Neper number, natural number, and it can be actually defined as a sequence 1 plus 1 over n to the power of n. And basically what this happens is that as you increase the n, inside the parentheses or the base goes approaches 1, but it's always greater than 1, but then the power approaches infinity. So something greater than 1 to an infinite, if it was exactly 1, no matter what the power was, we always get 1. But the difference here is that the base is not exactly 1, it's approaching 1, but it's always greater than 1. And we know that if we have a number greater than 1 and we raise it to a very large number, it gets bigger and bigger. So there are two things here that are competing against each other. One is as the base is getting closer to 1, which potentially decreases the value of the whole sequence. But then the power is also increasing more and more. And because the base is always kept at higher than 1, the value of the sequence should increase and increase. So these two eventually cancel each other out perfectly, and the resolution or the final result is a number, natural number, which is 2.7 something. Now, in order to implement the sequence, it's very easy to implement it in Java. What I'm going to do, I'm going to use a functional interface. So basically an interface with just one method that returns the value of the sequence. So let's head to Eclipse. I'm going to create a new Java project called demo sequence. And here I'm going to create an interface and call it sequence. And I'm going to annotate it with functional interface, functional interface, okay. And then what I'm going to do, I'm going to add a method which is basically returns the value. So going to have a double, so the return type is double because our sequence is from integer numbers mapping to double numbers or real numbers. Double evaluate, and the input is some integer k. Okay, so the main difference between a function and a sequence is that the input is an integer number here, not a double number. Okay. And then if I want to test this, so let's create a class test sequence, and I want to have a main method. So let's finish this. So here I'm going to create a sequence. So sequence, so the approach 1 for creating the sequence is to just have a sequence like S1 equals sequence 1 equals new sequence. And basically what I'm doing here, I'm using so this is the approach 1 is anonymous class, so we're implementing as an anonymous class, and just we're overriding the evaluate method, so we're going to return 1 over k squared, k times k, for example. All right, and then I can do a sysout, system.out print line sequence evaluate at some point 2. And we get 0. The reason we get 0 because we're dividing an integer by integer, so I have to turn this to double. 0.25, which is 1 over 4, correct. I can remove this, just k times k, and then we get 4, 2 times 2. All right, so this is the first approach. What is the second approach? Is to create a new class or implement sequence interface. So maybe we have some other, so I can create a concrete class, sequence example. So maybe we are implementing a particular sequence that has additional properties, because in the sequence interface we are just evaluating or returning the value of the or defining the function. This is just defining the function of the sequence or the expression. But here, for example, we can have a class here, implement sequence, okay, and then we are forced to implement the interface method, and we have to override it k times k. But we can do other things here, for example, such as overriding the toString method. So we go to source, override implement. We are going to override the toString method, and here I'm just going to return k2 or something like ak equals k squared. All right. So here now instead of using anonymous class, remember that we could also override the toString method when we're creating the anonymous class, but it's not recommended to have a lot of overridden methods, because it just doesn't make the text look nice, right? It makes the text of the code look ugly. But the good thing is that we can always refer a class when implement a sequence by its object type sequence, by its interface name. So sequence sec2 equals new sec example, for example. And then we do a sysout here, and sec2 evaluate at 2. So if I put double, it complains because Java doesn't do automated casting or downcasting, because there is a potential for error here. So I have to return 4, yes. But what I can do, I can also do a sysout on my sequence, and this invokes the toString method k squared. Okay, so this is just expression for the sequence. So for sequences that you may usually use you can implement them as a concrete class, but keep the signature or the footprint of the class as a sequence by just implementing our functional interface. All right. But then the third approach that I personally use the most is lambda expression, or basically it's a way of functional programming. And what I mean by that is I can define a sequence, say integer k goes to k times k. All right. So because it's a functional interface, which means it can only have one method, and then or one abstract method. It can have concrete methods, default methods, or static methods. So k times k, so you understand that the input is k and the output is k times k. And then I do a sysout on sec3 evaluate at 2, 4. Okay, so these are 3 ways, but this one is recommended because when we are passing this to another class, we can just simply use this. Wherever we need to pass a sequence, we can write this kind of expression and invoke the function directly. So this is a good advantage. And so this is the main concept of sequences. And another thing is recursive sequences. This also happens a lot in engineering or physics applications. In the recursive sequences, there is a factor of recursion, and by that we mean that each term of sequence is depending or is defined by the previous terms, or maybe the next terms, basically other terms. So an, for example, a Fibonacci sequence, in each term depends on the last two terms. In a geometric sequence, each term is the last term times a constant number. So R here is a constant number. R is a constant number. Okay? For factorial sequence, each term is the last term times the index of the current term. So here n is not a constant number. N is not a constant number. So this is the main difference between a geometric sequence and a factorial growth or a factorial sequence. Here the coefficient here is not a constant number. Now obviously, in order to find these, we can go back recursively. So we have an equals an minus 1 plus an minus 2, and then we can write an minus 1 equals an minus 2 plus an minus 3. So we backtrack all these to some initial condition or initial point. So all these recursive sequences need some initial points or initial conditions, and it depends on how many terms are appearing in the definition of the sequence. So for example, for Fibonacci, I have two terms that are defining the next term. So I need two initial conditions, and the initial conditions are typically a1 equals 1 and a2 equals 1. For geometric sequence, I have one term that is defining the next term. So obviously I need to set the value of r, but besides that, I only need one initial condition, and we typically say the a1 is some number, okay, the first term. For factorial, the same thing. So we only have one term that is defining the next term. So we typically use a0 equals 1, and actually we cannot do this, because if I put n0 here, we can do this, because if we start from a0, then the next term is a1. a1 is 1 times a0. So a1 and a0 are potentially equal. So for factorial, it doesn't matter, because a0 is equal to a1 by definition. Okay? So that's one of the reasons we can say that 0 factorial is also 1 factorial. And 1 factorial is 1, and therefore we can define 0 factorial as 1, 2. But I mean, obviously the best definition is to start from index 1. So recursive sequences can in fact have closed form solutions. In fact, this Fibonacci has closed form solution, geometric sequence has closed form solution, and actually for geometric is very simple. an is just a1 times r to the n minus 1 power, and you can easily verify that. And there are actually mathematical ways to calculate the closed form solution, if it's possible to calculate the closed form solution for recursive sequences. So if you're writing a Java code for recursive sequences, if it has closed form solution, it's better to implement those, because it just saves time. Typically recursive evaluation is costs time and memory, But if we have closed form solution, it's just substituting numbers into the equation and finding the value, and that's the fastest way, right? But if the closed form solution is hard to find, then we can directly implement recursion in Java. And I'm going to head back to Eclipse and show it to you. So let's create a new class, recursive sequence. Okay, and we're going to have a let's call it Fibonacci, for example. So let's go refactor, rename Fibonacci. Okay, and in the Fibonacci we can have private basically double. I mean, in terms of Fibonacci, all terms end up being integer. So private int, let's call it f0 and f1. These are the two terms, and we're going to initialize f0 to 1 and private int f1 equals 1. All right, so the first two terms are equal, are set to the respective initial conditions, and then let's implement our functional interface, the signature of sequence, because we so implement sequence, and then we need to add the unimplemented method or override it, which evaluates at some point k. So when we do the idea is that when we implement recursion, basically we have to start with the initial conditions, which are these are stop conditions for the recursion. Okay, so initial condition is that if k equals 0, so if k equals 0, then we can return f0. Okay, else if k equals 1, we still return f1. All right, so these are initial conditions. And finally, we actually don't need to have an else here, because it first checks these two and it has a return, so the method ends up terminating or going back. But I'm going to put the else here anyways. So if k is not 0 and not 1, I need to implement recursion. And the way we're going to implement recursion is just calling the function again, evaluate at k minus 1 plus evaluate at k minus 2. All right, this is how we implement the recursion. Okay, so this is the Fibonacci, and it implements our sequence. So let's head here, approach 3, approach 4, and note that I could actually so because Fibonacci has a identity, has a fixed definition, so we could implement everything in a static way. So we call the class and the static methods instead of trying to instantiate. So in this way, first let's call this a recursive sequence. So I can use the signature sequence, the interface fib, and then it's a Fibonacci sequence, an empty constructor. Okay, implement sequence. Well, let me see why it's complaining. Okay, so I was forgetting to write new. Okay, and then the signature, and we only want to evaluate this, so sysout or system out print line fib dot evaluate at 1, and then we can write a for loop for int I equals 0, I less than 20, I plus plus. We want to evaluate at index I. So now you see how the recursion happens. So we start with 1, the first term, the second term 1. As soon as it goes here in the evaluate method, basically it checks these two initial conditions. When these are returned, it returns the value, and then it goes inside another loop inside the evaluate. So it goes all the way down, and as you can see, if the number is large, going down in the evaluation function and then coming back pretty much takes a long time. So it's always recommended to implement, if we have a closed form solution for the sequence, it's better to implement a closed form solution. So here for the Fibonacci we have 1, 1, and then 2, 3, 5, 8, 13, 21. Now other sequences such as geometric, we can also implement that, but the question is, do I really need to create a class? Can I use a lambda? So lambda for recursive sequences. So let's say I create a sequence geom, and I want to go from k to something. So in order to do that, I'm going to go from k to some expressions here, and if k equals 0, I'm going to return or k equals 1. Let's start from the first term, is called 2, and then I'm just going to return, or let's just write an else, return what we want to do. We want to create a recursive. So 2 is the first term, and we know that at each k we have to multiply by the number. Let's say our the constant number is 3. This times evaluate, so we cannot call evaluate. Let's see if we can call evaluate function. We cannot. I call the k on this. So what did we do here? We created a lambda expression, but this lambda has a problem right now. So what we want to do with this lambda is be able to do a recursion right in the lambda expression. So in the lambda expression, we create a sequence object, and here we want to override the evaluate method. And in the evaluate method, what we can do is we want to have an initial condition and then some constant number times the evaluate method at some other point. Now the question is it possible to do that? And it should be possible, but I'm not sure if I recall how to do it. But for now, you can just instantiate a constant or create a concrete class, and basically just use the recursion in this fashion. Whenever you call the evaluate method, you check the initial conditions and then go inside the call the other evaluate method on the other terms. Okay, but if you have a, instead of recursion, if you have a definition or the definite expression for the sequence, you can definitely use lambda expressions. All right, so this concludes this discussion on sequences. Next we will have a look at series, and what is the definition of a series, and what are the, look at a few important series such as Fourier series, Taylor series. Thank you for watching. I'll see you in the next video.